Thank you, Ludovico. Thank you everybody for coming to my talk. I'm going to present the joint work with René Allerstorfer, Matthias Christandel, myself, Jon Nikita, Maris Ozels, Denis Rachet, and Philippe Verdun-Lunel. The outline of my talk is as follows. So first I will try to broadly motivate our project and present the main result. And then I would like to sketch the proof, but before I will be able to sketch the proof, I would need to introduce a couple of representation theoretic facts, namely the Schur, Weil, and Brouwer dualities, and also special elements called Eustace-Murphy elements. And after that, I will be able to sketch the proof, and finally, I will have a short discussion and present some open problems in that area. Okay, so what is monogamy? So monogamy is a rather broad concept, and for the purposes of this talk, I will understand it as a property of entanglement, which says that the entanglement cannot be freely shared. So the monogamy has different incarnations in quantum theory, and I would say that the most general form of studying monogamy is actually the problem, so-called quantum marginal problem. It's a notoriously difficult problem. For the one-body marginal problem, this was solved by Kleshko quite some time ago, and like two-body marginal problems and like in general k-body marginal problems are known to be QMA hard. And yeah, I want to put those references of Matthias Christandel and Michael Walter PhD thesis if you want to learn more about this. So studying in full generality is very hard, this problem, so I would like to focus on a very, very special case of this, which is known as G extendability, where G is some graph. And our work can be seen as a continuation of an old work by Wolf, Verstraete, and Srag from 2003. So what is a G extendability more precisely? So imagine you have some graph, and you have some bipartite symmetric quantum state sigma, and we say that this bipartite state sigma is G extendable if there exists a global state on a system, like on the global system, on the graph. So what I mean by this is that each vertex of the graph corresponds to some qubit. So think about this like that. And so extendability means that for all edges in the graph, those reduced marginals are actually equal to the sigma. So if you can find such a global state, we say that this sigma is G extendable. To formulate the problem more precisely, what we are going to do, we are going to somehow maximize, we want to maximize the bipartite entanglement on all the edges. And the way I would like to formulate it is in the form of the optimization problems, certain semi-definite programs. So I'll have 3 programs here. So let's fix some orthogonal projector pi, and you should think about this orthogonal projector pi as a projector in the on some subspace of the bipartite system, and this subspace has somehow a large entanglement. So yeah, if you look how the global state overlaps with a subspace on a certain edge, you want to make this value as high as possible. So the intuition you have in mind that by increasing this value p here, you kind of increase the entanglement on all the edges on this graph. And we formulate two seemingly two similar optimization problems here. So one is slightly weaker over here, as you can see. So here's like a strict equality, and here's we have inequality. And also we can formulate an average case problem for a given graph, right? So we just average all those overlaps on each edge. We can rewrite those optimization problems in the dual formulation. So in the dual formulation, those first two turns out to be equal to the following optimization. So you want to minimize the largest eigenvalue of a certain Hermitian operator. And here the minimization goes over choices of the couplings. So you can think about this object here as some kind of Hamiltonian, but you're allowed to tune couplings and you want to minimize those. So this tilde optimization is different from that optimization in a way that you put some additional restrictions onto those couplings over here. And for those of you who is interested in studying this, so we have a conjecture that actually those two things should be equal for arbitrary graphs, but we're not able to prove it. Okay, so let's. So I presented these optimizations for arbitrary graphs. Maybe we should restrict our attention to something tractable, more tractable. So let's consider the case of edge-transitive graphs. In that case, all the three optimizations are actually the same, and they're equivalent to studying the maximal eigenvalue of a Hamiltonian where all the couplings are the same. Another way we can think about this optimization or formulate a slightly different optimization problem is to consider some parameterized family of bipartite states. And then we would like to require that each marginal on the graph would be equal to this state. And we would like to maximize this parameter P. So the parameter P, again, you should think about it as being some quantification of entanglement of the state sigma. Again, this problem is too difficult in general, even for edge-transitive graphs. So for simplicity, let's consider the case where the graph is actually a complete graph. And this parameterized state sigma came from families of highly symmetric states. So let me explain both conditions in more detail. So just to motivate a bit why studying KN extendability is interesting, because this is related to so-called quantum definity theorems. So these quantum definity theorems appear in various contexts in quantum information. I just wanted to give you a couple of examples. So they appear in security proofs of quantum key distribution. They also appear in the study of ground energy approximations of local Hamiltonians by product states. And recent work also explores application of those quantum definity type theorems to a problem of relaxing the bilinear optimization problems into semi-definite programming form. And if you go back and look at the formulation of the quantum definity theorem for the bipartite case, you can equivalently restate it as follows. So the quantum definity theorem says that the state sigma is Kn extendable for every n if and only if you can write it in this form. So it states that the sigma is a more restricted version of a separable state. And this is also, you can contrast it to the a theorem called monogamy theorem, like a classical monogamy theorem, which states that the bipartite state is Kn(1) extendable for every n if and only if the state is separable. So it's an old result, and so you should think that quantum definity theorem corresponds to G extendability on the complete graph, and this classical monogamy theorem corresponds to G extendability on the star graph. Okay, so what are the highly symmetric states which we consider? So we consider three classes of highly symmetric states. So one is class is called Werner states. So the Werner states are defined in such a way that they commute with U tensor U for every unitary. We have another class of isotropic states. They are defined by putting the constraint that they commute with U bar tensor U. And on top of that, we also consider the case of Brouwer states. So namely, the states which commute with O tensor O, where O is an element of complex orthogonal group. We can rewrite those conditions in a bit different way, but equivalent way, by using certain projectors. And in order to introduce those projectors, let me first introduce those matrices. So the W matrix is a normalized projector onto the maximally entangled state. So I is just identity, and F is a swap or a flip operator. And then let's introduce the the projectors which we are going to need in order to rewrite those states in a bit nicer form. So I would need to have 3 projectors. So the first projector is a projector onto antisymmetric subspace, and the other 2 projectors, they come from the representation theory of orthogonal group. And yeah, so they both come from the symmetric subspace, but this projector is essentially a projector onto the EPR state. Using those projectors, we can equivalently say that the Werner states are defined like that. So you choose some parameter P, and then you consider a mixture of normalized projectors on the corresponding subspaces. So the Werner state looks like that. The Brouwer state will look like that. So here you can see that the Brouwer state is actually a 2-parameter family, not 1-parameter family. And also an important class of states are isotropic states, so they parameterize like that. So here we use this projector onto EPR pair. Also here, also use projector onto EPR pair, and here we focus onto projector onto antisymmetric subspace. So, and we would like to maximize those parameter P. So that's how our SDP will look like if we rewrite them using those definitions of those highly symmetric states. And the main result of our work is exact analytical calculation of those numbers. So it turns out that they look like that. So somehow before our work, exact values were not known. So there existed some numerical numerical research on them, yeah, and we were able to obtain exact formulas for every local dimension D and for every number of the systems. Okay, so before I explain how the proof goes, I would need to introduce some representation theoretic facts. So first I need to introduce the Schurwald duality. So the Schurwald duality is a classic result in representation theory, which essentially says that if you have a Hilbert space of n qubits, if you look at it as a representation of unitary group and symmetric group simultaneously, you can decompose it into direct sum of those tensor products of reducible representations of symmetric group and unitary group. So those blocks are labeled by mu, which is which come from a set of certain Young diagrams or partitions. So this notation means that mu is a partition of n, and you have some conditions that the size of the first column of the Young diagram is at most d. So what it means, let me show you by an example. So we can consider mu to be a partition, let's say 4, and then mu can look something like that as a Young diagram. And we can consider a transposition of mu, and this notation means that we extract the size of the first row, or equivalently, this is the size of the first column in the original mu diagram. There exists a similar duality called the Brouwer duality, which looks at this Hilbert space of n qubits as a representation of orthogonal group and a corresponding commutant of the orthogonal group, which is called Brouwer algebra. And here is a set of reducible representations, also labeled by Young diagrams, but now the condition is a bit different, as you can see over here. Another ingredient which I need to sketch our proofs is Eutis-Murphy elements. So Eutis-Murphy elements are special elements of symmetric group algebra and corresponding Brouwer algebra. So for symmetric group algebra, the case Eutis-Murphy element is a certain combination of simple transpositions. So this notation I comma k means that this is a permutation which permutes I and k systems. And we'd also need to consider the sums of those Eutis-Murphy elements. So if you take the sum, then you should think about this JS element as a sum of all possible transposition between all possible pairs. For the Brouwer algebra, those elements look very similar, except that you would need to add a certain element here, so I comma k bar. So this notation means that this corresponds to a projector onto the EPR state between I and k systems, and it acts as identity on everything else. And similarly, you can sum all those Eutis-Murphy elements. You get this JB element, which is a sum of those flip operators between all possible pairs, and minus the projectors onto the EPR state between all possible pairs. So we would like to understand the spectrum of those elements JS and JB, and it turns out that the spectrum is characterized by a very nice combinatorial object, which is called the content of a Young diagram. So I define it by example. So you can consider a lambda, which is a Young diagram of that sort. Then the content of the Young diagram are defined. The content of the boxes of the Young diagram lambda are defined as follows. So you took all the diagonals, and on the main diagonal you put zeros, and then if you go up in this kind of if you go up in the diagonal, you add 1 each time, and if you go below the main diagonal, you subtract 1. And then the content of the Young diagram is the sum of all contents of those boxes, right? So in that particular case, you can see that the content of this Young diagram is 1. And it turns out that the spectrum of Eutis-Murphy elements, or the summations of the Eutis-Murphy elements in different irreducible representations mu, for the symmetric group case, is given by the content of the mu, and for the Brouwer algebra case, for different irreducible representations lambda, is given by a bit more complicated formula, but still it's quite easy. So now I'm able to sketch the proofs of our main theorem. So let's consider first the Werner state case. In the Werner state case, we would like to write the dual SDP, and if you can massage the value of this p, the value of this p, into the following form, where you have a certain minimal eigenvalue, and this so you need to take the minimal eigenvalue of this JS element. And as I showed you before, we know actually the spectrum of JS, right? So it's given by the content. So what we need to do, we need to minimize this content. And if you have this visual understanding of the content, it's clear that the minimum is achieved for the most rectangular Young diagram possible, right? So because you want to make the columns, each column as big as possible, but we have this restriction that the size of each column is at most d. So we would like to make each column essentially equal to d. But there might be some leftover, which is given by this k number, which is n modulo d. And then the optimal Young diagram is characterized by these formulas. And then you can just plug these formulas into here, and you obtain the formula for the optimal value in the Werner state case, which I showed you in our main theorem. For the Brouwer state case, the story is similar. You can write the dual SDP, and then it turns out that the value of this dual SDP is equal to the maximal eigenvalue of the difference now of this JS and JB element. And it's easy to see that those elements actually commute, and we know their spectrum. And if you add some more representation theory to that, you can obtain actually the full solution to that. And finally, the most difficult case is a tropic state case. It turns out that in that case, the problem of finding P reduces to this optimization over here. So you want to take the minimal value over a certain piecewise linear function, and this piecewise linear function is comprised from the certain affine functions. And these affine functions are parameterized by certain pairs of the irreps of symmetric group in the Brouwer algebra. But you don't take all possible pairs. There is a certain set, and the set has a rather complicated description, but you can study the set, and then you can understand how this piecewise linear function actually looks like. And I just want to give you an impression that we have a situation like that. So you have a bunch of affine functions, you take the maximum, and then you would like to understand where this minimum lives. Yeah, so it's a bit delicate story, but it's possible to do. And once you do it, you obtain the formulas which I showed you in our main theorem. So let me quickly discuss some other results. So there exists a very nice work from the previous year on extendability of the complete bipartite graphs. And in that work, they managed to obtain the formula for isotropic state cases. It looked rather simple. Unfortunately, the formula for Werner state does not have a nice general expression. So it's basically an open problem to find a nice expression here. But for star graphs, it's known, and it has a rather simple formula. And I should say that this specific formula was recently used in a lot of papers on quantum maxcut. And we feel that our results may help into finding and studying other approximation algorithms in that context. It would be interesting to consider some other H-transitive graphs as well as some other groups, right? So what about, for example, symplectic group case? So with that, I would like to thank you for your attention.
Okay, we have some time for questions. Please remember to stand up and go to the mic. Okay. Anybody? I can start. So if you go back to this conjecture that you had at the beginning, so can you elaborate a bit on what's kind of the main difficulty there? Because it kind of seemed very intuitive. But just naive understanding. Yeah, sorry.
Yes, over here.
That
yes.
One. What is pi e first? I missed that.
Yes. So basically, what is the optimization here, right? So you can see that the graph, you put the same projector onto each edge in the graph, and then you have a variable, right, which you can tune, and then you want to minimize the maximal eigenvalue of all such of a space of such Hamiltonians. So here you see you want to impose an additional condition that this coupling is non-negative, but here you don't have such a restriction. Yeah. So intuitively and numerically, we seen that they are the same. We try to prove it without success. I don't know what techniques are needed in order to prove that.
But pi e is generic, or?
You mean the graph?
Pi, the projector.
I guess for the projector, we are thinking that it's we suspect it can be generic. Yeah, it can be generic, but you can try to prove it for certain specific cases. Maybe, I don't know, rank 1 projectors or rank 2 projectors, or whatever. But we are thinking that if you just say that it's orthogonal projector on each edge is the same, this might be true. Yeah.
Okay, thanks.